Here we have example number 6. So we're given the function f of x is equal to 2 over x squared, and we're told to find the Taylor series of this function centered at a is equal to 2. Then we need to find where that representation is valid, which is the same thing as the interval of convergence, and use the alternating series estimation theorem to determine how many terms are needed of like a partial sum or of a Taylor polynomial in order to approximate f of 3 with an error smaller than 4%. So based on just the definition of Taylor series, we know that the series we want is going to look like this. So this is fn, so like the nth derivative of f evaluated at 2, because we're centered at 2, over n factorial, and then x minus 2 to the power of n. So from here then, all we need to do is to produce an expression for that nth derivative evaluated at 2 and plug it in. To do this, one thing that we can do is start by taking derivatives, as many as we need, just to figure out a pattern to define that general nth derivative. So if we take our function f of x and we look at the derivatives, we can see a bit of a pattern. So if we write f of x as 2 times x to the negative 2, we see that every time we apply the power rule, we collect more integers in front, which looks like a factorial. And so you can see here that the general pattern looks to be that our nth derivative is negative 1 to the n times 2 times n plus 1 factorial over x to the n plus 2. You can kind of go through that yourself just to kind of convince yourself that it works. But after kind of making that guess at the nth derivative, it's a good idea to check that the next one still works too. So taking our third derivative and looking at the fourth, we see that we still have 2 times n plus 1 factorial times x to the negative 6, where 6 would be our n plus 2, so it still fits the pattern. That's good. And so then that means that this is a good formula for our nth derivative. Now, if you want to, you can prove that this is true using induction. But I'm going to just say now that I don't think, for ones that are like this, where it's a pretty simple pattern, where we're just kind of seeing some integers collect as factorials, I don't think you will be asked to prove this kind of thing by induction for assignments and exams. Like we trust that you can make these inferences. So now that we have our nice formula for the general nth derivative of our function at x, we plug in 2 because our series is supposed to be centered at 2, and that derivative that we get then is this. So plugging in 2 for x on the bottom here, that cancels out with the 2 on top, one of them, so you just have negative 1 to the n plus 1 factorial over 2n plus 1. We plug that into the template star above. That's just this general formula that I wrote out, and we get that the Taylor series is this. So n from 0 to infinity of negative 1 to the n plus 1 over 2n plus 1 times x minus 2 to the n. So you'll see that the initial formula had the n factorial on the bottom, and then n plus 1 factorial on the top, and so those kind of almost totally canceled out other than an extra n plus 1 on the top. And so that's how we get this. Oh, Jesus, sorry, my cat tried to sit on the screen. Okay, so for part B then, to find the interval of convergence, or the interval where our representation is valid, we use the ratio test. So we take our n plus 1 term, divided by an, take the absolute value, business as usual. So remember, an plus 1 refers to the entirety of what's inside the sum. Oh, that's not an plus 1, that's just an. There we go. So if we take an plus 1, that's just replacing the n with n plus 1. So here n plus 1 becomes n plus 2, and so on. Divide that by an, which is just the term as usual, Dividing it, we just multiply by the reciprocal. And after letting everything cancel out, we end up with absolute value of x minus 2 over 2. We can take this outside of the limit because you've got the limit only depends on n, not x. The limit that we're left with is equal to 1, so that means that the ratio test just gives us absolute value of x minus 2 over 2. Now by the ratio test, if that number that we're left with is less than 1, then our series will converge. So we set up that inequality and we end up with x is between 0 and 4. Because the ratio test doesn't tell us anything about when the limit is equal to 1, that corresponds to checking these endpoints of the interval. So that's why we have to check 0 and 4. Both of them end up giving us things that have n on the top, so clearly the general term of like the sequence will go to infinity, so both divergent. So we can conclude that the interval is just 0 to 4. Finally, for part 3, or part C I mean, we wanted to, yeah that's right, so we want to approximate f of 3 with error smaller than 4%. So what we'll do is we'll plug 3 as x into our series and look at a bunch of terms. If we want our error to be less than 4%, we're going to look until we find 1 over 50. Uh-oh. I have to fix this. One over 25. Okay. So we're trying to find terms that are less than 4%. Yeah. So if we look at a bunch of terms of the series and calculate them out, we're looking for ones that are less than 1 over 25. Then, by the alternating series estimation theorem, we can just exclude every term like from there on. And so looking at some of these fractions, this one is going to be about 10%, and that's just because I'm comparing it to 6 over 60. 7 over 120 is going to be kind of 5% because I'm comparing it to 7 over 140. But then this one, 1 over 32, we know for sure this is less than 4% because 32 is bigger than 25, so that's going to be our upper bound for the remainder. And so because this then is the first term that we can exclude, our approximation is enough if we only look at the first 7 terms.